Section P.3, radicals and rational exponents. These problems that I am going to do, they're going to be on this worksheet that we already went over, but I wasn't able to finish all the problems because I forgot that we hadn't finished this section, so here they are in this video list. Rationalizing the denominator. Rationalizing a denominator is the process that you use for getting rid of the radical from the bottom part of a fraction. So to get rid of this radical from the bottom part of a fraction, you're going to do something that is called the conjugate. The conjugate of this expression is going to be 4 minus the square root of 5. In other words, you see how the expression at the bottom is the sum of a real number, the 4, and an expression that has a radical. All you're going to do is change the sign on the radical part. If it is 4 plus the radical, then 4 minus the radical is the conjugate. Or 4 minus the radical, 4 plus the radical is the conjugate. All you're going to do is basically change the sign in the middle or in front of the radical, right? And you're going to use that expression to multiply top and bottom of your fraction. So you're going to multiply across numerator times numerator, denominator times denominator. So 8 times 4 minus the square root of 5 is the numerator. Denominator is going to be 4 plus the square root of 5 times 4 minus the square root of 5. So then now we have to focus on simplifying this. And my main focus right now is going to be simplifying the denominator. I'll come back to the numerator in a little bit. So 4 times 4 is 16. We're going to FOIL the denominator. 4 times negative square root of 5 minus 4 square root of 5. Then square root of 5 times 4, positive 4 square root of 5. And square root of 5 times the negative square root of 5, negative square root of 25. So you see, we multiply together, numbers that are inside of square roots. It's okay to multiply them together as the 5 and the 5. But it's not okay to do 4 times the square root of 5 and say it's 20. If 4 is not inside of a square root, when you multiply times the square root of 5, you just put them side by side. That's as much as you can do. So then, I'm gonna continue focusing right now on simplifying my denominator. I'll come back to the numerator later. So I'm gonna bring down the 16, and then if you notice here, negative 4 square root of 5 plus 4 square root of 5, they're the same term but the opposite sign, so they cancel each other. You bring down the minus, the square root of 25 is something that you could simplify, and that's going to be 5, has a perfect square root, right? And then 8 times 4 minus the square root of 5 over 16 minus 5 is 11. So either we leave the answer as you see it, or we could rewrite it as distributing the 4. 8 times 4 is 32 minus 8 square root of 5 over 11. So both are correct answers, either this way or this way. You want to distribute or you don't need to distribute. Okay? That would be the answer for this. And that's rationalizing the denominator. It's the process to get rid of a radical from the denominator. It could be on the numerator, but not at the bottom. And we use the conjugate, which is the pair of this expression. Okay? So this is a complex number. What you see on the denominator in complex numbers have always this pair that is called the conjugate, where only the part that is the radical has the sign of it is going to change to the opposite. Okay? Only that. For the next problem, we're simplifying this multiplication. So here you are going to use, and I put a dot, and there's an X there. I should put that multiplication symbol, not a dot. So we're going to use the product rule. The product rule says that if you have two radicals multiplying times each other and the indexes are the same, you could rewrite this as multiplying these two numbers inside of a single radical versus 2. So now we're going to see how we can simplify this. So we're trying to see if 64 is a perfect fifth root number, if it has a perfect fifth root. So for example, 1 to the fifth means 1 by itself multiplied by itself 5 times, right, which is 1. 2 to the fifth power 2 times 2 is 4. 4 times another 2 is 8. 8 times another 2 is 16. 16 times another 2 would be 32. Let's see, 3 to the 5th power. 3 times 3 is 9. 9 times 3 is 27. 27 times another 3 is 81. And 81 times 3 is 243. So you can see that 64 is not a perfect square root number, but it's between 32 and 243. 64 is divisible by 32, because you want to go backwards looking for a number that is divisible by. So we're going to rewrite it. The 5th root of, divide 64 by 32, and that's going to give you 2. So the multiplication of 2 times 32 is the same as 64, right? Now we apply the product rule again. And let me erase this. So 5th root of 2 times the 5th root of 32. So 5th root of 32 times the 5th root of 32 is actually something that we had done here before. We found it. It's 2. And then we just rewrite the answer. 2 5th root of 2. I'm sorry, I put a 32. 2. That would be the answer. Okay, and the 5, the little 5 here is not the exponent of the 2 on the outside of the radical. It's the index on the root, right? So that would be the answer for this. This next one is a simple problem where you're going to apply the quotient rule. The quotient rule says that if you have a single radical and there's a division inside of this radical, and by the way, this root is a cube root, you could easily break this apart to work it by pieces. Work with a radical on the numerator, a radical on the denominator. So these two numbers have a perfect cube root. The cube root of 125 would be 5, because if you do 5 by itself, if you multiply it by itself 3 times, it gives you 125. The cube root of 27 would be 3, because if you multiply 3 by itself 3 times, it equals 27. So that's it. That would be the answer of this. So we just use the quotient rule, and make sure you notice that it's not a square root, it's a cube root what you're doing. Now here, you have the subtraction of these two radical expressions. So the focus right now is going to be doing something about the 81. Remember that we can only add or subtract radical expressions together if they have the same radical, the same radicand, inside. The radicand has to be the same, but in this case, these two are not the same. 3 probably, there's nothing we can do about it. Such a small number. But 81, it's a number that we could probably factor it out. If you try to find if it has, first of all, a perfect cube root, 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is going to be 64, 5 to the third is 125. So it doesn't have a perfect cube root, but 81 is identified as being between 64 and 125. So the first number that 81 would be divisible by is 27, going backwards on this list. So 3 cube root of, now when you divide 81 by 27, that gives you 3. So you're going to factor the 81 into the multiplication of 3 times 27. Minus, you just copy the other expression. Now you're going to apply the product rule here. You're going to break apart this radical into 2. Okay, and these 3 things are supposed to be multiplying together. And then you copy the expression that's being subtracted. So we're going to simplify this part. 3 times the cube root of 3 times 3, because that's the cube root of 27. We had just found it before. Minus 4 cube root of 3. All we're going to do is simplify this expression a little bit. You are able to multiply these two coefficients. 3 times 3 is 9. Cube root of 3, and now you're going to subtract minus 4 cube root of 3. And so now you're able to actually perform the subtraction between these two terms because they have like radicals here. So 9 minus 4 is 5 cube root of 3. And that would be our answer. Okay? So we can only add and subtract radicals together if they have the same expression inside, or same number inside of the radical. Otherwise, we need to do all of this to make them the same. So this next objective says, understand and use rational exponents. So for simplifying, and the instruction here is simplifying, right? So for simplifying this, we're going to use one rule. This rule says, if you have something or an expression raised to a fraction, to a rational exponent, rational is a fraction. You could simplify this by rewriting it in a radical, where this n is going to become, this denominator on the fraction is going to become the index on the radical. The 1 could be the exponent here inside of the expression of the radical, or you could also use it as the exponent outside of the entire expression. You could enclose everything in a parenthesis and raise it to the first power. Either way, it's correct. Sometimes it's more convenient to put the exponent inside or outside for the simplification purposes. Although, in this particular rule, the numerator is always going to be 1. Raising something to the first power, whether it's inside or outside of this expression, it's not going to change a thing. It's not going to affect anything at all. Something raised to the first power is itself. So then, technically the 1 has not much to do here. It's not of big importance here. The important thing is the denominator, to place it on as the index of the root, right? So we're going to change this into radical, -8 goes inside. The denominator is going to become my index. And the 1, since I'm telling you that you may put it here inside as the exponent of the -8 or outside, but honestly it's not going to make a difference. I'm not even going to write it down. When the numerator is 1, let's just ignore it. So cube root of -8, it's a perfect cube root, -2. Why? Because you're looking for something times something times something, that when you multiply this, and it has to be the same thing times the same thing times the same thing 3 times, it equals this number. And that would only be given by -2 times -2, it's 4. 4 times a -2, it's a -8. Okay. And so that would be our answer, -2. Just write the answer one time. You don't need to write it 3 times, right? That's the reason why that answer is the answer. Next problem is simplify this. Okay, so there's 2 rules that I need to tell you or make you aware before we attempt to solve this problem. So let me move this a little bit here. So these 2 rules are the following. One is that something very similar as what you did right now in the previous rule. You could rewrite this as a radical where the 8 goes inside, the n is going to be the index, and the m is going to be either the exponent inside, or remember that you could also rewrite this as 8 goes inside. Let me write the 8 in here. The n still, this is going to go as the index, the denominator. But the other way, remember that it could be written, the m is outside. Now this time, the numerator, the m, is going to be not a 1, but a different number every time. So that's one rule. Another rule that we're going to need to use in this problem is the fact that you see that we have a negative exponent. So whenever you have something raised to a negative exponent, you can change that exponent from being negative to now being positive by creating a fraction. You're going to flip around this fraction. Flipping around this fraction is doing the reciprocal of the fraction. So by you doing that, the exponent changes to positive. Okay? Every time you have a problem like this one, and you see there's a negative exponent, whether it's a fraction or not, if it is negative, the first thing you want to do is this second rule. You want to change the fact that this has a negative exponent. Make it positive. So the only way you're going to do that is think as if this was 32/1 and flip that fraction around. And by you doing that, let me write it bigger so that the fraction can fit better. The only way you're going to be able to change the negative exponent is by doing this reciprocal and changing the exponent. Sorry about my dog. Sorry, so I don't know if you heard, but my dogs were barking like crazy because there was someone outside. So I did the reciprocal on the fraction, and by doing that, now this exponent can now be turned into a positive exponent. So then I applied that rule for changing the negative exponent into a positive. The next rule we're going to use is this first one that I talked to you about. Change the denominator into a radical expression. So now you're going to put the fifth root, the denominator is going to be the index of 32, and this 2, you have two options. Either you use it as the exponent of the 32 inside of the radical, or you put it outside as the exponent of the entire expression. That's the best thing you can do. If you put it inside, you're going to have to raise the 32 to the second power first, and that's going to be such a big number. 32 times 32, huge number. Then you would have to find the fifth root of that number. I don't think you want to go through that. It's better if you just put the 2 outside. You'll see how simple it's going to be right now. So 1 over, start always by simplifying the inside of this parenthesis expression. So the fifth root of 32, we've done it in other problems. We did it over here. This one. Fifth root of 32 was 2, right? You can see y here. So then I'm going to say 2, it's the simplification of the inside, and then that 2, you're going to raise it to the second power. So the final answer is going to be 1/4. 2 to the second power is 4. So then here is the answer for this problem. Okay? These are the two rules you need to know. Next problem. Okay, for this one, I'm going to tell you a few rules before I even attempt to do this problem. These are basic rules, basic algebra, and these rules are called rules for exponents. Exponents. So, I'm going to show you with examples. These rules for exponents, obviously they're going to tell us how to deal with the exponents. X to the second times x to the third. If you have two bases, base is anything that is raised to an exponent. Two bases that are multiplying times one another, the exponents get added. When the bases are like bases, they have to be the same to each other, and they're multiplying times one another, you add the exponents. What's going to happen if you are dividing like bases? You're supposed to subtract the top exponent minus the bottom exponent, and that becomes the new exponent of that base. Another rule says that when you have multiple exponents for a single base, you are supposed to multiply the exponents together. Another rule says that if you have, let's say, x, y raised to the third power, multiple things inside of a parenthesis. First of all, they're multiplying times one another inside. Even if you don't see any symbol, they are. So then you could assign this exponent for each of these two variables inside. Okay. The other rule is that anything that's raised to the 0 power, the answer is always 1. And the last rule is something that we have done right now in the previous problem, that anything raised to a negative exponent could be changed to a positive exponent by doing the reciprocal of the fraction, 1 over x raised to the n power. So these are rules for exponents, and they just guide us through how to simplify an expression with exponents. These rules, I want to clarify, are not for dealing with coefficients, with the numbers in front of the variables. Okay? If you're dividing, you divide the big numbers of the 20 and the 5 here in this case on this problem. If you're multiplying, you multiply. This is just for the little numbers on the variables. So here we have to simplify, and we have this fraction, so we're dividing 20 by 5, that would be 4. These two x's are dividing by one another, and they have exponents, so I'm going to apply the second rule. We're going to subtract the top exponent minus the bottom exponent to come up with a single exponent for this x. Now, how to subtract an integer, how to add or subtract integers with fractions. You're going to turn this fraction into this integer into a fraction. How? You're going to multiply the integer times the denominator of the fraction. In this case, it's a 2, right? So you're going to say 4 times 2 is 8. 8 halves, because you're trying to turn this 4 into a fraction with the same denominator as the other one. So whatever the denominator is of that second fraction, that's always what you're going to put for your fraction. So now you have 4 raised to the 8 halves minus 3 halves. All you have to do is subtract the top numbers. 8 minus 3 is 5. The denominators never subtract from one another. You just write it down. You just pass the denominator down. So that would be your simplification. 4x raised to the 5 halves. Okay? So you need to study very well these rules, because at any point you may have a problem dealing with that. Last problem. simplifying this radical expression. So the only way to simplify this is going to be through rewriting this as a rational exponent. So you're going to be using this rule, as a matter of fact, this one right here at the very top on the corner. Okay? But now we're going backwards. So this rule that we talked about, okay, that could be the m here, or could be, we don't need the brace, or could be with the m inside, as the exponent inside. Both are correct ways. So here what we're going to do is we're going to go, we have something as with a radical. As a matter of fact, this looks like this expression. So we're going to go to this side of the equals and we're going to rewrite it in this format. So we're going to say, okay, x raised to the, notice how here the index is the denominator of the fraction, the exponent inside is the numerator. That's what we're going to do. 3 over 6 becomes the exponent here. Now, what can you do here? Well, 3 is not divisible by 6, but 3 and 6 both get divided by 3, and that's the way to reduce them. So that would be 1 over 3. Next, since your original problem was given with a radical, I say write it back as a radical. So you're going to leave the x inside. You are going backwards again now from this form to this form. That's basically what you're doing. So the denominator, it's going to be the index in the radical, and the 1, you may put it here inside or outside, but I'm going to tell you that I'm not even going to write it because when the exponent is 1, it's not necessary to write it down, and it looks better if you don't. So then this would be our final answer, cube root of x. So this concludes these few problems that I missed in section P.3. Hope you find them helpful. Okay.